Okay, so we're going to start off today, and probability is a whole science in mathematics. It's a whole field by itself, and it's associated with stochastic processes or probability. And probability is just the chance that something happens. And a lot of times, well, humans don't understand probability for one thing. It's for example, back in 2016, when the election was going on, and when they did all the polling, there are these sites that predict who's going to win. And last year, as this year, the results are exactly the same. Right before the election, they were predicting that Hillary Clinton had a 75% chance of winning the election, and Donald Trump only had a 25% chance of winning. And it was based on the polling and the Electoral College of all the states. And because of the polling at that time, where it was showing that Hillary Clinton was leading Trump in various states, some of those states went to Hillary Clinton. And but it's all based on the likelihood of the right voters coming out and so on. So going in, everybody thought that Hillary Clinton was going to win the election back in 2016. Because Trump only had a 25% chance and Hillary had a 75% chance. Well, you know what the outcome was. And Donald Trump won the election. And, you know, we shouldn't be surprised, because we can't say if the probability is 25%, 75% that Hillary Clinton's going to win. What we have to say is in you know, like 100 elections like this, Donald Trump would win 25 of them, and Hillary Clinton would win 75 of them. So if you were a betting person, you would bet on Hillary Clinton. And again, you would have lost that bet. Well, it turns out that in this election, the results are almost identical. And they're predicting now that Joe Biden has a 75% chance to win this election based on the polling. But the polling as we get closer to the election is more important. So we talk about probabilities in terms of percentages. There's a 70% chance, 75% chance. If you were a betting person right now, you would bet that because Joe Biden has a 75% chance of winning, you would probably bet on Joe Biden. And 3 out of 4 times you'd be correct. But there's always that outside chance, that 1 in 4 chance that Donald Trump is going to win again. So, and there could be some problems with polling and so on. It's almost going to be a certainty at this point that Joe Biden will win once again. The Democrat will win the popular vote. So Hillary Clinton got 3 million more votes than Donald Trump in the last election. It's probably going to be at least that in this election. But as you know, the Electoral College is what determines the election. And so we'll have to wait, and please get out there and vote. So probability is the chance that something would happen, and we usually write the answers as a decimal. So when anybody asks you what is the probability of something, you need to report a number between 0 and 1. All probabilities are numbers between 0 and 1. Could even be equal to 0, could be equal to 1, but it's the probability of anything. Now, if you have a probability between 0 and 1, that say is 0.25, then the way that we would interpret that probability is we would convert, just like we convert decimals to percentages, we would convert the decimal number, which is the probability, to a percentage. And we would interpret the probability with a percentage. So 25% of likely voters will vote for Donald Trump is what this, it's going to be more than 25% of likely voters, of course. Donald Trump has a 25% chance of winning. And so Donald Trump's probably going to get 47% of the vote, and Joe Biden might get, 51% of the vote, or 49. Okay, but I say this not with absolute confidence. I say this there's just a chance. It's likely. All right, so all of your answers today, when they ask you for probabilities, they're going to be numbers between 0 and 1. Like you can write the fraction version. Sometimes in games of chance, we write fractions. Other times we write decimals. So one of the skills that you're going to have to bring to this section is this ability to convert between fractions and percents and decimals. Okay, a big number that you want, when we calculate a fraction in a lot of settings, the probability is just a numerator and a denominator. And we define the numerator as being the number of ways that some event can happen, like Donald Trump winning the election. And the bottom number is the set of all possible outcomes. And we need to be able to determine both of those numbers in any given problem. And so they introduced tree diagrams as one way to decide the total number of items. And so let me show you an example of how that would work. And these are, I think, in the notes when you read them. The first example, an ice cream parlor claims to have more than 14 possible sundaes. And their slogan is, try a new one every day for 2 weeks. Two brothers visit the shop to test out this claim, and they are presented with the following menu. And so they have to choose either 1 scoop or 2 scoop. So that's one decision they make. There are 2 possibilities. Then they have to choose the ice cream flavor. There's no mixing and matching here. You either get all vanilla, all chocolate, or all strawberry, and you can only pick one. So there are 3 choices of ice cream flavor that you can select. And then they throw something on the top, something sweet like rainbow sprinkles or fudge sauce on the top. And you must get one of those on your sundae. And there are 2 possibilities there. Now, if we do a tree diagram, this is what it would look like. The number of scoops, 1 or 2. And this is a way to try to chart every single possible outcomes because we need this number to calculate a probability. The ice cream, notice they have vanilla, chocolate, and strawberry written twice. One time if you have 1 scoop, and then these flavor or these sundaes over here are different than these sundaes over here, even though they involve the same flavor ice cream, because this sundae involves 1 scoop, and these sundaes involve 2 scoops. So completely different. And then when you get down to the toppings, notice you've got rainbow sprinkles or fudge sauce written 1, 2, 3, 4, 5, 6 different times, because we want to chart every possible outcome. So if you count all the possible outcomes that you have, and I'm counting out just these smallest leaves at the outermost bounds of the tree diagram, there are 12 different possibilities. It just so happens that if you take 12 or 2 and multiply by 3 and multiply by another 2, you get 12. And that's exactly the number of possible sundaes that you can get at this place. So this is called the multiplication principle. And if you have to make 3 choices, determine how many possibilities are for each choice, and then multiply those numbers together. That's one way to determine how many possibilities there are. And so if they said you can have a new flavor or a new different kind for 2 weeks, it's not quite true. You can make it almost 2 weeks, but there's only 12 days worth of different sundaes, according to this. All right, so we're going to get now into the definition. We'll give it to you. And the first one is called a relative frequency method. And here's the formula for that. So I'm going to give you this definition, and then we're going to go calculate a probability from that previous context. So this is the definition of a theoretical probability. It's the kind of probability that we use when we're working with probabilities in, say, games of chance or something like that. Casino games, lotteries, that sort of thing. This notation here, and we have all kinds of notation in mathematics, this P of A, that means the probability that event A will occur. And so then we count the number of ways A can occur and put the number of ways that A can occur on the top. And then we have to know something about we call it an experiment. In the experiment in our previous problem was going to the store and buying a sundae. And in the bottom, in context, the bottom number would be the total number of different sundaes that you can get. So here's the example. The brothers in the first example try the lucky sundae, and that's where an employee will choose the sundae for them. And then here's the question that you're going to see a lot in this section. What is the probability that? So immediately you know that the answer you write down has to be a number between 0 and 1. So you're not going to write 23. If the probability is 0.23, you're not going to write 23% because that technically would be wrong. What is the probability that the brothers will end up with, 2 scoop with chocolate ice cream and fudge sauce? What is the probability? So we go back and we say, okay, of the 12 total possible sundaes, how many of them are as is described. If we were to write them all down, it would look like this. I'm going to call rainbow sprinkles R and fudge sundae F. And I'm going to call the ice creams V, C, and S. And I'm going to call the one just so I can have some different characters. So if we were to write down all of the possible outcomes, the first one would be a single scoop with vanilla ice cream and rainbow sprinkles. The next one would be one scoop with vanilla ice cream and fudge sauce. Now, if I continued this, I would have a listing of 12 different outcomes that kind of look like this. The next one would be one CR and then one CF and then one SR and one SF. So that would be the 6 on this side. Get the idea? How many of those outcomes of these 12 would be the outcome where you have 2 scoops, chocolate ice cream, and fudge sauce sundae sauce, fudge sauce sundae? How many of them do you see are exactly like that? Just the one. Let's see if we can find it. It's 2 scoops, so it's over here. Chocolate ice cream, so we're coming down here, and fudge sauce. It would be the 2 CF outcome. There's only one of those. All of these sundaes are unique, but there's only one. So the probability of A is equal to 1 because there's only one sundae that matches our criteria, matches our what we call an event, matches our event. And then we have the total number of possible sundaes is 12. So there you see the probability is 1/12. And we use the counting principle to count up that or figure out what that bottom number is. Doesn't always work like this, but in this example, it does. All right, what about this one here? What is the probability that they will have a sundae? I'll call this one event B. We usually use capital letters to represent our events. How many of these outcomes, get it on there again, how many outcomes will have a sundae with strawberry ice cream? Strawberry, it would be these 2 because they have an S in the middle, and there are a couple over here, 2SR and 2SF. Oops. Oh. Anyway, there's 1, 2, 3, 4 of them that have an S in them, which means that they have strawberry ice cream. So what is the probability that they will have a sundae with strawberry ice cream? These 4 have strawberry ice cream. None of the others do. So the top number, 4 of the sundaes have strawberry ice cream. 4 have chocolate, 4 have vanilla, right? Out of 12 total. And normally what we'll do is reduce the fraction if we can. So we would say the probability is 1/3. We'll be working with tree diagrams and when we get to the conditional probability section a little later. All right, let's go on to another. In this experiment, we're going to roll a die and then we're going to flip a coin. And we can do them sequentially or we can do them one at a time. It doesn't really matter. We're going to record the face of the coin, and it could be a head or a tail. And then we're going to record the outcome on the die. Now I'm talking about, a die is a singular of dice, right? So there's 6-sided number cubes that you throw, and on the 6 sides you have the numbers 1, 2, 3, 4, 5, 6, usually with dots. And so there are 6 possible die rolls, 1, 2, 3, 4, 5, 6. And then the coin toss is head and tail. So at each branching of the coin toss, there are 2 possible outcomes that we can have for the coin. So we have to count 2 different outcomes. And here are the total number, or here are the listed outcomes, just like I listed in our previous example, 1CR, that kind of thing. It's much shorter now. So this outcome right here is a 1 with a head, a 1 with a tail, a 2 with a head, a 2 with a tail. How many outcomes are there here? And I see some of you are typing in the chat. That's helpful. Okay, yeah, very good. So that 12 then becomes the bottom number. Now we only have to do is figure out of these 12, how many are described in the event, in the probability that we're trying to calculate. So let's go to this one here. And this is the notation that we're going to, that I'm using, pretty common. Because of the capital P on the outside, you would say, what is the probability of, and then you might have to read something into this. What's the probability of getting ahead? how many of these outcomes are and contain a head? Okay, that's right, 6. So the top number is 6, and then the bottom number is the total number of possible outcomes, which in this case is 12 again. And you probably knew this before we calculated this right now, because you have a half of a probability of getting a head is 1/2. Now, if we would interpret that probability, we would say, I see 50% is as one of the answers. We would say that there's a 50% chance that we would flip a head as our coin toss. All right, this one here means what's the probability of getting a 6? And of course, that's referring to the roll on the die. So how many outcomes of those 12 contain a 6? No. Yep, right there. There's a 6 and there's a 6. There are 2 of them that contain a 6 out of the 12 total outcomes. So the probability of getting a 6, reduce the fraction and get 1/6. Now let's put those 2 together. What's the probability of getting a head and a 6? Another way to say that would be, what's the probability of getting a 6 and a head? Like that. How many are there? Just that one. Just that one. Very good. And there are 12 total. And finally, the last one, what's the probability of getting a 7? Yeah, there are no 7s. So there are 0 ways to get a 7 out of the 12 outcomes, or we just simply write 0 for that one. And this has a special name in probability. When you see the 0, this means that this event is impossible. On the other end, the largest number of probability can be, that's 1. That would be 12 out of 12 in this case. And we would say that if the probability is 1, then that's a certainty. That means that the event will definitely occur. What's the probability that the die roll is less than 10? Well, all of these die numbers range from 1 to 6, so they're all less than 10. So all 12 out of 12, and we call that a certainty. It definitely will occur. Okay, so for this tree diagram here, these are called roots, and all of these here are called branches. And if you deal with these conditional probabilities in the future, in the next couple of days, we're actually going to write a probability on that branch. All right, so we can extend the thinking to include another event. If we toss a second coin, how many outcomes do you think we would have? This might take a little bit. So let's say that our experiment is first roll the die, next flip the coin, and then flip another coin. If you wrote down the tree diagram for that, how many possible outcomes would there be? You can go ahead and write the answer in the chat. Okay, and I'm not seeing anything. When you roll the die, how many possibilities are there? Just roll the die. 6. Good. When you flip a coin, how many possible outcomes are there? Good. 2. And when you flip the other coin, how many possibilities are there? And if you use this fundamental counting principle, how many outcomes do you think there would be? 6 times 2 times 2 equals 24. So then if we calculate any probabilities in this setting, we're going to have that bottom number be 24 instead of 12. Let me go back and show you what those 24 look like. So all I have to do is add the other coin toss here. And then you could get a 1 and then a head. And then when you flip the next coin, you can either get a head or a tail. And you're either going to get a head or a tail branching out from all of these 12 outcomes. Well, if you have another branching that goes out where there's 2 outcomes, you can see that in the end, if you count these up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and there's your 24. But you can just use that counting principle to find them. Yeah, and sometimes there's going to be too many outcomes in order for you to draw a reasonable looking tree diagram. So, we're not going to do this brute force way of counting anymore, but instead we're going to use this counting principle. All right, so let's see if you can do it. It's similar to the ice cream example, but this one is pizza now. Now what you can get on your pizza, or what you can order on your pizza, you can order the size. There's 3 different sizes. You can order your sauce, either a garlic sauce or a marinara sauce. 2 possibilities there. Then you get to choose your cheese, mozzarella, provolone, parmesan. 3 choices there. And then you've got a single topping, right? So you can select one of these 6 toppings. They say they have over 100 possible combinations of pizza. Is that correct? All right, so I see a lot of 108s, and some say no. But yeah, if you multiply those numbers together, let's see, that's 6 times 3, that's 18 times 6. And 18 times 6 is 108. So yeah, they do have more than 100 possible pizza combinations. So now let's throw in some probabilities. What is the probability that a randomly selected pizza, out of those 108 possible pizzas, selected by a group of friends, will have pepperoni on it? How many pizzas have pepperoni? And I'll abbreviate that probability like this. Well, we need 2 numbers. We need, of all those 108, that's going to be our bottom number, of all of those 108 possible pizzas, how many of them have pepperoni? Yeah, so we can count these in the same way. So just imagine that there is only 1 possibility for topping. So instead of 6, we had just 1. If we make sure that the pizza has pepperoni on it, it can have any one of these other combinations of size, sauce, and cheese. So you can have, if your pizza has pepperoni on it, that doesn't impact the decision for the size. You can have a large, a medium, and a small pepperoni pizza. You can have 2 different possibilities of garlic, of sauce, garlic or marinara, as long as you're going to have pepperoni at the end. And you can have 3 different kinds of cheese, as long as you have pepperoni at the end. And you must have, in that last one, there's only 1 option because you must select pepperoni, but it can have all these others. So the answer was 18, which is correct. And some of you even simplified it and got 1/6. See, so you can see when the probability simplifies to a simple fraction like this, probably they're going to want you to write your final answer as a fraction. Because if you wrote the decimal, then you got it like 16.1666, then you've got rounding issues, so that you have to address. Okay, when I saw this problem in the homework, I was thinking, wow, this is one that normally appears later on, but because they're making a big jump because they're actually putting probabilities on here. So this R here means red, and this B means blue, and you can see a Venn diagram. It says a bag contains red and blue marbles, red and blue. You draw a marble from the bag, here's the bag, and the way I'm going to indicate that you have red and blue marbles in there is I will indicate with reds. But they don't tell us how many are in there. But notice these 2 fractions. The probability of getting a red on the first selection is 4 out of 6. And the probability of getting a blue is equal to 2/6. Now, based on those fractions, you can maybe guess. Now, the way that this experiment is working is you're going to draw a marble out and then another marble. But you're not going to take the first marble and put it back in the bag before you draw the second one. You want to just grab 2 marbles and leave, and in your hand you have 2 marbles. And so this first one is the first draw. And this other set of red and blues down here correspond to the second marble out of the bag. Notice that the denominator here, the bottom number, which means kind of the total number of outcomes, after your first selection, when you select that second marble, the number of total outcomes goes down by 1. So it goes to 5. So here's the first question. How many marbles do you think were in the bag to begin with? And then you pick one out, and then you're going to pick again. And after you pick that first one out and it's sitting in your hand, how many marbles are left in the bag if this is your probability that you're going to get? Okay. Yeah, it might be. I'm just going to go ahead and do this one, and you can see if it makes sense. If the probability of getting a red on the first draw is 4 out of 6, there are probably 4 red ones in there to draw from. And since the probability of getting a blue is 2 out of 6, there's probably 2 blue ones in there. Does that make sense? So if you reach in the bag and you pull one out, since there are 4 reds, 6 total, the probability of getting a red on that first draw is 4/6. Similarly, if you reach in and you grab one of these balls that you cannot see at random, since there are 2 blue ones, the probability of getting a blue on the first draw is 2/6. All right, now here's where the tricky part of the tree diagram comes in. Because if you're going down this branch, that means that the first marble that you selected was red. And so just imagine that you selected this red, and then now it's sitting in your hand and it's no longer in the bag. So if that one's gone, now what's the probability of getting a red? 3 reds to choose from, 5 total. The probability is 3/5. Good. I think some of you are picking up on this. And then after you select the red one, so this red one is out of here, on the second ball, the probability of getting a blue, well, there's 2 blues left, 5 total, so 2/5. All right, let's back up again. Let's say instead, we're coming down this branch, and that means that the first marble that you selected was blue, and so now there's 1 fewer blue marble in the bag, which means there's just 1 blue marble left in the bag, and there are 5 total marbles left in the bag. So the probability of getting a red one on the second draw, there are 4 red marbles and 5 total, so the probability is 4/5. And then the probability of getting a blue, since there's only 1 blue, 1 out of 5. And that completes the tree diagram. And once you have all those probabilities on those branches, you can calculate some interesting things. Here's how we would extend the and list all of the possible outcomes here. And so this is the first example that you're going to have where you're listing all the outcomes where the probabilities are not quite the same. So here are the outcomes and then the probabilities. The possible outcomes would be if you come down this branch, red and then red, or you can do red and then blue. And I'm just going to abbreviate them with letters. If you choose this other path, blue first and then red, that's a different outcome than red, blue, even though one of them is red and one of the marbles is blue. And then finally, what's the chance of getting 2 blues? And it turns out, you'll see this later, but they give you this example for one reason, or for some reason in this section, so I wanted to do one of them. To get the probability, we're going to multiply the probabilities along the branch. So if we have red, 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 we follow this branch, and we take those 2 probabilities and multiply them together. And you do that for each of the 4 outcomes. There's not that many, so we can list them all. If you go red and then blue, that's following this path. So you multiply 4/6 times 2/5. And I won't reduce these yet. Blue and then red. What is the fraction? Simplified fraction. Here's blue and then red. Blue and then red. So it's 2/6 times 4/5. All I'm doing is multiplying, fraction arithmetic, but multiplying across. Okay, some of you had 8/30ths, good. And then finally, the blue, 2/6 and 1/5, and that's 2/30. What you'll find here is that the sum of all the probabilities will be equal to 1. In this case, it's 30/30, which reduces to 1. Answering their questions based on the diagram, how many red marbles and blue marbles were in the bag? Well, we had 4 red and 2 blue. And then based on the diagram, what is the probability of getting 1 red marble and 1 blue marble in any order? So here's red, blue, and here's red and blue. So here are 2 outcomes that involve red and blue. In this case, the red comes first, then the blue is selected. In this one, the blue comes first, then the red is selected. So we have 2 of our possible outcomes. This one doesn't match our criteria, and this one doesn't match our criteria. So what we do is we add those 2 together, 8/30ths plus 8/30ths, and that's equal to 16/30ths. And then you can reduce that to 8/15ths. So it turns out that the probability is 8/15ths. All right, we do have many of these games of chance where all of the outcomes are equally likely. And we've already done one where that was the case. Every one of those outcomes, when we flip a coin and roll a die, they're all equally likely to occur. No one's going to occur more than the others. On the other hand, in this example, we have 4 outcomes. The smallest one is the blue-blue. And so you're less likely to get a blue-blue combination, because what you'd be required to do is, without looking, picking out both of those blue marbles from the bag. And that's a very unlikely occurrence if there's only 2 blue and 4 red. So these outcomes are not equally likely. You'll have experiments where you do have equally likely outcomes, and you'll have experiments where you don't have equally likely outcomes. Okay, so in this section, they kind of repeat some of the things that we've already done. For example, you can see that the probability of some event is a number between 0 and 1. And we interpret probabilities as percentages. There are many games of chance where the outcomes are equally likely, and we're going to use our same probability formula up here. So in order to use this, you have to let A be an event. You need to count the possible total number of outcomes, and then among those possible number of outcomes, count the number of ways that your specific event A can occur. So basically, all of this here is just describing this formula. All right, so I'm including this in the lecture notes, and you can read it. So now I want to get to some examples. Okay, at the start of a football game, a referee flips a fair coin once, awarding the ball to the team that guesses the correct coin face showing, heads or tails. What's the probability of flipping a head? When you flip a coin, how many possible outcomes are there? And what are those outcomes? Heads, tails, 2. So that's the bottom number. And of those 2, heads or tails, which one matches your event? How many match your event? How many of those outcomes are heads? 1. So the probability of getting a head is 1/2. Probability of getting a tail is 1/2. 50% chance of getting a head. In this next grouping, a single die is rolled. The outcomes, there they are. They've written them in roster form, 1, 2, 3, 4, 5, 6. All of the denominators of the probabilities that they ask you, find the probability of rolling a 5. How many 5s are there? Just 1. How many total possible outcomes are there? 6. Probability is 1/6. Probability that the number is greater than 3. I'll just use n for number. So all of these will have a denominator of 6 in this experiment. So all you have to do is to figure out how many outcomes are in the event. How many numbers are greater than 3? 3. 4, 5, and 6. How many numbers are greater than 4? 2. And I'll just reduce these along the way. What's the probability of getting a number less than 8? How many different numbers are there in our set that are less than 8? Okay, good. This is the one where you get 6 over 6, so this is a certainty. You're certain to get a number less than 8 when you when you roll the die one time. And what about number greater than 8? So no such numbers. Good. All right, so rolling a die is a game of chance. I'm not talking about, Keno or blackjack and one of those, even though those are games of chance as well. The next application that you might have some familiarity with is the cards example. And so there are 52 cards, and half of them are red. The diamonds and the hearts are red. No, you can't see that on my graphic here. And half of the cards are black, spades and clubs. And then you have 13 number cards. And instead of a 1, we use an ace. And then you got 2, 3, 4, all the way up to 10 number cards. And then Jack sometimes is thought of as the 11, and the Queen is the 12, and the King is the 13. So there's 13 cards. The Jacks and the Queens and the Kings, they're called picture cards or face cards because they've got a face of some figure on there. And so since there are 3 face cards in every what we call suit, 12 total face cards. All right, now the experiment down here, given that this is the context, you are dealt a single card, 1 card. So it's like randomly selecting a card out of the deck. Find the probability of being dealt on that 1 card a jack. So there's 2 numbers you need. You need the number of jacks in that deck, and you need the total number of cards in the deck that you're drawing from or being dealt from. How many jacks are there? Okay. Jack of hearts, jack of clubs, jack of diamonds, jack of spades. So there are 4 jacks. And how many total cards are there in the deck? Yeah, 52. And this reduces to 1/13. Okay, a diamond. The diamond, these suits are arranged these rows are arranged by suits. So you can see something that looks like a diamond there. It's actually a rhombus. We call it in geometry, but yeah, it's a diamond. All these are diamonds. We have 13 of the 52. Or you can say exactly 1/4 of the cards are diamonds. 25% of the cards are diamonds. In fact, every one of these probabilities, since you're being dealt a single card out of the deck, the bottom number of your probability will be 52. Now all you have to do is figure out how many cards are your event. How many cards are greater than 3 and at the same time less than 7. Okay, so 4s are greater than 3 and less than 7. 5s are greater than 3 and less than 7. And 6s are greater than 3 and less than 7. Now we wouldn't want to include 3s and 7s here because it did say between. So 4s, 5s, and 6s. And there are 4 of each of those. So you are correct, 12. 3 different card numbers, but there are 4 of them each. All right, so, and this simplifies to 3/13. By the way, your calculator does fractions pretty well. If you take 12 and divide by 52, and then go up here to the math menu and select the very first option, which is arrow convert to fraction. So it looks like this. So take 12 divided by 52 and convert it to a fraction. And the beauty of this is it reduces them at the same time. So the reduced version, let's say on this example that we did before, if I divide the top and the bottom by 4, no, I can't do that. How about 6, 2/5? So I can do something like this. 4 divided by 6 times 3 divided by 5, convert to fraction. You get the reduced version. Okay, what's the numerator of number 18? What number goes on the top? 1, because of all those 52, just that card right there, just one of them is the ace of clubs. So 1 out of 52, that's less than a 2% chance. Very unlikely that you'll receive the ace of clubs if one card is dealt to you. A card with a green heart. Okay, so we only have black and red cards, so no greens. Games of chance, cards are considered in that. Here's a scenario where 2 dice are rolled. And when you roll 2 dice, you can get 2 1s, which would make a sum of 2. And you can get 2 12s, which makes the sum of, or 2 6s that makes the sum of 12. So the outcomes will range from 2 up to 12. But those outcomes are not equally likely because you're much more likely to get a 7 than you are a 2. So I want to give you another format for this in case they ask you probabilities about sums. So a lot of times in a lot of games that you play, if you roll the 2 dice, you don't think of it as a 2 and a 1. You think of it as a 3 because you add the 2 die together and then you move 3 spots or whatever it is. But because of pluses here, we're going to take both of those 2 numbers and add them together. So 1 and 1 is 2. 2 and 1 is 3. 1 and 3 is 4. So add the number in the row heading and the column heading together to get each of these numbers. After a while, you'll definitely see a pattern. So you can see just by looking at all 36 outcomes, you just counted up all the blue numbers there, you would actually see 36 different numbers. And you can also see that only one of those numbers would give you a 12. So it's very unusual to roll what we call boxcars, which is 2 6s. There's only a 1 in 36 chance to do it. Similarly, there's only one way to get a 2, and that's if you get a 1 and a 1. Okay, so some probabilities in this context, they'll ask like this. What is the probability of getting 2 odd numbers? A single die is rolled twice. 36 equally likely outcomes are shown. 2 different representations of the experiment. Okay, so go count the 36, because out of the 36, how many of them contain 2 odd numbers? Odd in the mathematical sense, like 1s and 3s and 5s. So when you roll a die, you can have the odd numbers are 1, 3, and 5. The even numbers are 2, 4, and 6. So which of these rolls give you both odds? Oh, there's 1, and there's 1, both odd. And there's 1, so 3 in the first row. You can ignore everything in the second row because you have an even number, a 2. And if you have a 2 in there, then you can't have two odd numbers. So 3 in the first one, and 4, and 5, and 6. None in the row 4 because you have a 4. Same thing with the 6. You're not going to have two odd numbers in any of the 2, 4, 6 row. So 3 and 3, and 1, 2, 3. Okay, good. Looks like you're picking it up. And we would reduce this to 1/4. Two numbers whose sum is 6 is the next one. So if you're going to do this one, then it might make more sense to come down to this chart, because this chart involves the sums and not just the pairs. So how many 6s do you count here? And they all appear on the diagonal, right? There are 5 of them. And that fraction doesn't reduce, so we just write it as 5. Two numbers whose sum is less than 13. How many of these are less than 13? Yes, very good, 36. So this is the one where it's a certainty.